Comes on everyone. Let's start off. Hope everyone has tried the homework problems. Chal, comes on everyone. So, anyone got any answers? Let's see. The first one. So, we stop the Earth from rotating and we want to find in how many days the Earth is going to get destroyed. Perfect. Okay, let's start with this. 1/4 नहीं रह सम्यक. Now, how do we do this? So, first thing, right? You cannot integrate this. And you can't take any force and you can't integrate and you can't get the time here. So we are going to use Kepler's law. So we are going to actually, manipulate that Kepler's law to get this thing. So listen to this concept. So the idea is this. Instead of saying the velocity became zero, right? Let's, change the velocity slowly. Let's say the speed is, not suddenly decreased, but imagine if it had decreased little. So initially you would be going in a circle and your speed was, so this was the sun here and this was your speed v. Let's say the speed decreases gradually. Right? It starts going in an elliptical orbit. Remember, if your speed is v orbit, you will go in a circle. We wrote this in trajectories, if you remember. If your speed is anything less than v orbit, you start becoming an ellipse. So the moment you decrease the speed, you actually go in an ellipse. Perfect. And because of this, let me show you how it would look. So let's say if you decrease it little, you would go in an ellipse like this. And if you decrease little more, you will go in an ellipse like this. You can see what is happening here. And as v tends to 0, you will get almost a straight line. Like, I know it will go and collide, but imagine if it doesn't collide, you will almost go in a straight line. And this black one is a case when v tends to 0. You can clearly see the length of the major axis is decreasing. As v tends to 0, we get an ellipse. So technically speaking, if v becomes 0, it becomes a straight line. But mathematically, we can say, don't put 0, get very close to 0. We get an ellipse whose minor axis b is tending to 0. So when v becomes 0, it becomes a straight line. V tending to 0 becomes a line. So indirectly, what we're saying is a line is nothing but an ellipse with a minor axis 0. This story is clear so far. Any doubts on this story there? So if you keep decreasing the speed little, you'll get ellipse, and as v tends to 0, you get a line. Now the whole question has become like this. Initially, your orbit was this, a radius r. And when you just stopped the particle and it started going in a circle, now this is the orbit. This is the scenario when v tends to 0. So for this orbit, the red one, the major axis is r. This is the major axis of the orbit. And for the initial one, 2r is the major axis. So basically the length of the major axis becomes r from 2r. Length of the major axis goes from 2r to r. So far clear? So indirectly you have created two ellipses basically. One is a circle and one is this. Then Then you're done. And we know for an elliptical orbit, the time period t square is proportional to a cube. So t square by t1 square by t2 square is equal to a1 cube by a2 cube. So initially t1 is nothing but 1 year. That is 365 ka square, and this is t2 ka square. Initially a1 was r, and this was r by 2 ka whole cube. And that would be 8. And the t2 would be 365 by 2 root 2. And this is not the answer. Because what is t2? T2 is the total time period. Isn't it? T2 is the time for full trip. But once you stop it, you will go and hit the Earth, sun, and you're done. So for the Earth to go into the sun, you will take only half of this time. Time is half of T2, which is 365 by 4 root 2. This thing comes to around 65 days. Yeah, you got 2 months. Yeah, but I think within 15 days, the temperature on the Earth would go beyond 100 to 150 degrees, and we'll get fried anyway. We really don't have 2 months. Maybe you'll have maximum 15 days. And anyway, it feels like that only nowadays in summer, isn't it? We are getting closer and closer to the sun. Any doubts on this? This is a standard model. You should definitely know how to do this thing. This thing has come in mains also before. Mains and bits, these kind of things will pop up. Right? If you see, once you know the idea, it is not really that difficult to solve, but getting an idea that I can use Kepler's law was the catch. So, yeah. Any doubts on this?
So in this question, the speed is immediately stopping, right? So
Yeah,
like small elliptical orbits which were there, those won't come right directly. Even there.
they won't come. That is just for our discussion. Na? We are seeing what would have happened if you don't stop it, but if you decrease the speed little, how it would have looked. Yeah. Why did I take half, Advai? Because this T2 is the time period for one full trip. The question is only for half of the trip, so you take half. Devanshi, Naisha, clear with this? Anvita, Shaurya, clear? Tanishka, Ashvi, got it? Now, based on this, I made up this question. This is also based on what I taught you right now. It is exactly that same concept. But that's what I'm saying. See, Max really does not understand whether you're talking about a particle or as long as the equations look same, they would feel the same. So let's see how will this compare to the other one. How can I solve this using Kepler's law? Now, let's say at some point, let the distance be x. If you look at the forces on the particles, this guy would be gm2m by x square. This also will be gm2m by x square. Right, and from here we can get the acceleration. This is a2 and this is a1. Yeah, this can be calculated. So a1 will be 2gm by x square. A2 will be gm by x square. Perfect. Now what I'm suggesting, yeah, we can do from center of mass frame also, because if you see in this scenario, center of mass does not move. But we can even do better. Now, what I'm suggesting, go and stand on any one of them. Let's go and stand on 2m. So you go and stand on 2m. So this is with respect to 2m. If you ask this person, boss, what is happening to m? What will he say? He will say, okay, there is a gravitational force on it, which is a 2gm square by x square. Plus, since I am accelerating, remember this is a non-inertial frame. If an observer is standing on a frame which is accelerating, we have to apply a pseudo force. He will say, okay, I am on a non-inertial frame, so I'll also apply a pseudo force, which is mass of the body, and the acceleration of the observer in the opposite direction. So this is your pseudo force. So this person will think, okay, so this person will feel as if the net force acting on this particle, how much is A2? A2 was gm by x square, so that would be 3 gm square by x square. So far, story is clear. The person standing on 2m will think there is a net force of, because A2 is this guy, there is a force of 3 gm square by x square acting on him. This is what he will always see. All clear so far? And now we are going to convert this into the previous problem. So if you just look at the equation mathematically, forget about the planets and everything, and just look at that equation, it gives you a feeling as if there is a planet of mass 3m. This is a planet which is fixed. And there is a satellite of mass m, right? And what was the initial distance between them? The initial distance was d, and this guy was going in a circle. Isn't that how this equation looks? F is equal to g m 3m by d square. Isn't this how it looks? Everyone agrees with this? So the whole logic is this. Max really does not understand what is gravity. Max does not know what is center of mass. Max does not know what is relative velocity. It doesn't care about what you want to call it. Max simply will say, since the equations are looking identical, both the scenarios are same. So what I'm suggesting, the person on 2m, this guy will think this is a particle which is rotating around a planet of mass 3m. And iska time period I can calculate, which is 2 pi by root 3gm. If you guys remember the time period of a planet, d power 3 by 2. If this was a planet going around, this would have been the time. Everyone agrees with this? And now we are saying this guy is coming straight towards him and colliding. Now the question has become, what if it is not rotating, but if velocity is 0, then this will go straight like an ellipse, and same scenario, if v tends to 0, this becomes an elliptical orbit. So initially it used to go in a circle. Now it became an elliptical orbit. This distance was d, and this distance was 2d. So the major axis has become half. Now, doesn't this question look exactly like this question? Are you clear with this? Simple thing is, will Max know the difference? Does Max care whether the 3m is a particle or a pseudo force or what? Max does not care, and that's the best thing about the Max. Max will say, as long as you look same, I really don't care what you are. It is not a racist. Max is pure. And we physics people are manipulative. You just take every damn thing and say they look same, so answers match ho jayega. And then, yeah, we use the same logic. So we will say T1 square by T2 square is equal to A1 cube by A2 cube. And then initially time T1, so we know this was your T1. So T1 will be, this guy is d by 2 ka whole power 3 by 2 and T2. This is 2 pi by root over 3 gm d power 3 by 2. This is 2 power 3 by 2 into time T2. So we get T2 from here. But again, remember, we don't need the full time. We need only half of the time. That is 2 will cancel. We end up with pi by root 2 root 3 gm d power 3 by 2. This is for full oscillation of full time period. This is for full orbit. We need only half of it. So time to meet is T2 by 2. This would be a proper advanced paragraph level question or difficult. Matlab, it's very difficult to think that you can think of in terms of Kepler. Did you observe? We didn't use any integration, nothing. And I'm saying this is a mains question. This is actually mains question, question 17. You can modify this to be something of this sort. You can play this game. Uh, Again, I'm telling you, please make sure tomorrow take a rough paper and just do it for 5 minutes. Because now when you listen to this, it'll feel like, oh, okay, I understood. But trust me, if you do it tomorrow, you won't be able to put the steps. You'll get confused like, यहाँ पे क्या डालना था? Oh, यहाँ पे क्या करना चाहिए था? That confusion will come. So it's not because you didn't understand. It's because your brain didn't register. Because I did all the work here. You guys just listen to it like a movie. It is like going to a gym and the trainer is lifting the weights and you're asking, oh, where is my six pack? You're not going to get it. You didn't lift anything there. All clear with this? It's a pretty good one. What about this one? This is another solid question. And that is the reason I gave you them as a homework. I wanted you to think. It's okay if you didn't get it. But how do we approach, like, this is what happens in advance. There is a big shock factor. You see a question, you feel like, what the hell? And anyway, advanced, you have that bandwidth, no one is asking you to score 100%. Advanced, you put 50%, you will still end up with a very good rank. So how do we work this? How do you take 3m mass? Because the equation which I got is 3gm square by this thing. So that is g into m into 3m. Right? So that is like gm1 m2 by r square. That's how it looks. How do we do this? Now again, this we need to know the results what we did, for elliptical orbit. One thing is clear, this is going in an ellipse. So let's find the initial energy first of all. So what is the energy of this satellite? The energy of this satellite is potential energy plus kinetic energy, which is minus g capital M by small r, plus the kinetic energy is half mv square, that is gmm by r. You end up with minus gmm by 2r. This is the energy of this elliptical orbit. But we also know the energy of an elliptical orbit is minus gmm by 2a. We proved this. This thing has come from this problem. This guy. Page 61. So that means we proved, so whatever ellipse that you got here, that ellipse ka major axis is 2r. Right? So the major axis 2a is 2r. Great. So we proved a is equal to r. This comes from the data what is given. So if that speed had been different, this would have been different. Perfect. And we also know the center of the planet is the focus for this ellipse. That comes from Kepler's first law. Any particle that is going in elliptical orbit, the planet will be at the focus. Center of the planet is the focus. Now you should know something about ellipse. If you look at this, so from focus F2A and F2B, these both are R and R. And we got A is equal to 2R. So where are these 2 points exactly? So in an ellipse, there is only one position where this can occur. When you draw an ellipse, in case someone does not know the properties of an ellipse, the property of an ellipse is this. If you take the two focuses, let's say F1 and F2, and you choose any random point on the ellipse, F1P plus F2P is always equal to 2A. This is the locus of an ellipse. All the points, the distance of one point from the two focuses, the sum is always equal to 2A. All these points will lie on a focus. And now here what we got F1. So from the focus FA plus FB, we got 2A. This will occur only at one position, that is at the minor axis. So the elliptical orbit which we got, the planet, the focus, this must have been A and this must have been B, because this is R and this is R. Is that making sense? So the line AB was the minor axis. We just proved all this. So you should know the elliptical orbit energy, and then you should know little about ellipse. And now if you look at this, so when you launch it from here, this guy was going something like this, and you ended up here. Technically speaking, this would have been a full ellipse like this. Something of this sort. This was the focus. I didn't draw the minor axis properly. This was the minor axis A and B. So what I need to find is actually this area. If I can find the area of this triangle, and if I can find the area of this half piece, my job's done. This is R, this is R, this is 90 degrees. It all comes from geometry here. So the area of this triangle will be half into R into R. The area of this part of the ellipse, hope you remember, area of an ellipse pi AB got 2. That is half of the area of the ellipse. Right? And what is the beta value here? We can clearly see AB is your minor axis, which is R root 2, which is nothing but 2B. So beta value is R by root 2. So this is pi, A ka value is R, and B ka value is R by root 2. So we got the total area of this FAB, that part, is R square by 2 plus pi R square by 2 root 2. This is the total area from the focus and this. Why am I finding the area? Do you guys remember this? The aerial velocity is constant. So that means, can I argue like this? Since the aerial velocity is constant, for an area pi AB, you will take a full time period T, which is 2 pi root gm A power 3 by 2. Then the question becomes unitary method. So this is pi by 2 R square R square by 2 1 plus pi by root 2. इसके लिए time कितना होगा? You can simply use unitary method and finish it off. Are you clear with this? Because I know the total area, I know the total time. So for full area, if we take this much time, for this much area, how much time will it take? Then this would be 2 pi root gm. A is anyway R power 3 by 2. Right, into R square 1 plus pi by root 2 by pi AB. A is again R and B is again R by root 2. Yeah, it looks weird and big, but this is solvable. R square goes off. You end up with 2 pi root gm. You can send the pi also inside. There is one root 2 also sitting there. So that would be a root 2 by pi plus 1. You get something like this. This was your capital T. That was your initial time period. Are you clear with the steps? You seriously don't know why AFP was 90 degrees? Such a big question. Out of all the concepts you could have asked, the one you wanted to ask was, why is this angle 90 degrees? This is the pole. This is the equator. So if you draw a line from the pole and from the equator, that's a 90 degrees. It's a right angle triangle. Happy? Yeah, great. All clear with this? Pretty good stuff. Getting it. Uh, it's completely fine if you don't get it. But the point is this. I'm not saying they'll ask the same question in the exam also. The thing is, you learned how to connect different things and you could have seen this thing. Like, maybe they'll ask you a part of it somewhere. So we don't know. But there, you can play around like this. You can actually find time for these elliptical orbits and look at these questions like these things you couldn't do normally. But Kepler's law, you can really play around like this. Clear with this? That's what I said. Gravitation, we have some really solid ones. We couldn't do all these things in electro. We could have done, but but Kepler's law was there. There, with that, we are done with gravitation. Right? So gravitation and electro both together are one combined chapter. Treat them like that. Whatever you could have done in gravi, you could have done everything in electro. In electro, the difference was we had dipoles. Here we don't have dipoles. Here we did more satellites. There we didn't do anything about satellites. So that's the only difference if you ask me. Everything else will be the same. We did almost 18 questions. Out of the 18, I think at least 1/3 of them were solid advanced paragraph level questions. So spend some time. It's a good one. So there. So with that, we're done with this thing. So you should start solving your material, gravitation, try to wrap up, take 1 week, and next Thursday, finish off solving. Don't delay it anymore. The next thing is Gauss law. This is another interesting chapter. Antimatter act like negative. There's nothing like, see, for example, if you take an electron, the antimatter of it is called a positron, which has a positive charge. You have a proton with a positive charge. The antimatter of proton is called an antiproton, which has a negative charge. You even have an anti-neutron. Doesn't have a charge, but its property is different. It has some magnetic thing is reversed. So they're a little weird. Let's not worry about it. Yeah, they have still mass, right? There is nothing called anti-mass. Anyway, so what is Gauss law? Now, this is another important chapter, right? So this is like most related to the electrostatics. So let's see. So first thing we will define something new called electric flux. So this is a completely new word. We will hear something similar called magnetic flux later on. The idea is the same. Electric flux, the symbol we use is phi, a circle with a slash. If I have to give you a little context, flux simply means anything that goes through an area is called flux. If let's say water is flowing through an area, we call it water flux. If people are passing through an area, we call it people flux. Right? So flux is simply any quantity that's passing through an area. As simple as that. Right? But when we say electric flux, we will talk about when field lines pass through this. So electric flux, it's proportional to, if magnetic field lines pass through an area, we call it magnetic flux. So if gravitational field lines pass, we call it gravitational flux. So flux is just a very generic word. It simply tells you about some quantity passing through an area. So electric flux is proportional to number of field lines, electric field lines, passing through an area. That's a straightforward definition, a very powerful definition, right? It looks very simple and all, but we are going to use this a lot. Meaning, if you have two surfaces and if the number of lines passing are same, that's it. The flux is same. It doesn't matter how, what, and anything, right? So others do keep your cams on. So if you take some areas, let's say if I take a small area, if I take a big area, if I take something like this. So let's say field lines are going like this. Let's say field lines are going like this. Let's say one line is coming like this. So here, if you see, there are 5 lines. There are 5 lines. Here it is 6 minus 1. That is 5 lines. So net 5 lines are passing. All of them have same flux. It doesn't matter at what angle the lines will go. It doesn't matter what is the area. Nothing. Number of lines is flux. As simple as that. Clear with this. Right? If someone is typing anything to me, please type here to the co-host. Okay. There are 2 logins, host and co-host. So I can't see you if you're typing any answers. So flux is field dot area. Now we will think about this. We are defining it in a different way. Now, how do we calculate flux mathematically? So when we calculate flux mathematically, it's given by integral E dot dA, right? Where E is your electric field. A is your area vector. Right? So that is your definition for flux if you want to calculate. But wait, it looks like a contradiction. Let's talk about it. Suppose if your E bar is constant, then it comes out of the integral. Then your flux becomes simply E bar dot A bar. That means if you have an area, this is your area vector. This is a field, let's say, and this is angle theta. So the flux is simply EA cos theta. Now look at this thing. Just now I said it doesn't depend on area, it doesn't depend on angles. Now I'm saying suddenly it depends on area and angles. So what's happening? No, it's not about opposite lines cancel out. It is like number of lines crossing, right? If one person enters and one person leaves, can you tell the difference between 2 lines? So they look the same. So what is the catch here? So the catch is this. What is electric field? You guys remember how we defined electric field? The number of lines per unit area. Yeah. If you have more lines in a unit area, there is more field. That means look at this formula now. If I write this thing as E dot dA, if electric field is number of lines per unit area will cancel, you get number of lines. So we are not contradicting. Getting it? The thing is, if you study flux in terms of field lines, so it all depends on how you want to study this. So if we study flux in terms of field lines, it doesn't depend on angles and areas. Flux is independent of area and angle. But if you study flux in terms of electric field, so be careful, electric field and field lines are not same. They're completely two different things. Field lines per unit area, right? Crossing, that's called field. So if we study in terms of field, so we're not contradicting. So the importance is like how you want to study. If you study in terms of electric field, then flux depends on area and angle. Both are important. So one will give you a mathematical way. So if I know the field, I can find the flux. You can put on this thing in the red box if you need. That's it. This is the only formula we have, integral E dot d. We're going to play with this today. We're just going to play with this one thing for today's. And that will lay a foundation for us next. So any doubt so far? Anything you're not clear? Anyone? You can always unmute and ask if there's any confusion. Or if you're feeling shy, you can always type. But don't feel shy, ask. All clear with this? Great. So how do we take this area vector? Now, for closed figures, if you remember, this we discussed in vectors, the very first chapter actually. We did a small discussion there, but let's do it again. So for closed figures, we take outward normals as positive. Just a convention. We take outward normals as positive. Means if you have a closed figure like a sphere, or if you have a closed surface like a cube, we take these things as positive, the area vector. It's like the ball is full of spikes. That is how the area vector will look. Area vector is perpendicular to the surface and away from it. So for this, we will take these things as positive. There will be 6 vectors, right? Each face will have an area vector. But let's say if you have an open surface like a disk, then you can choose a bar however you want. Generally, we like to keep the flux as a positive thing. So we take an acute angle. For open surfaces, we choose E bar, or on the side of choose A bar in the side of E bar. Again, this is a random convention. So suppose if you have a disk like this, I can take the area vector right side or left side. So, but let's say field is this way. So just to make an acute angle, we will define the area vector as this way. This is arbitrary. Since anyway it is a scalar quantity, let's keep it positive. So clear with this, we already know how to get the electric field. So how to get the area vector? If it is a closed figure, take outward normals. If it is any open surface means what? It is not closed, as simple as that. Then area vector, and how to calculate flux? E bar dot dA, the integral. So if your field is variable, use the integration. If field is constant, then directly you can do E bar dot A bar. Clear with this? So this one in the red box is the actual formula. If E is constant, then the formula becomes E bar dot A bar. So E bar dot A bar is a special case. You won't be so lucky like every time you'll have field constant. All got this? So let's take up some small ones and then we'll slowly build it up. That's it. Huh? Yeah, I just taught you only one new thing called electric flux, which is simply integral E dot A. Bus. Mathematically, we are not doing anything hi-fi out of it. So let's say we got a cube. X, Y, and Z. The side of the cube is A. Let's name them. This is phase 1, phase 2, phase 3, phase 4, phase 5, and phase 6. So 5 is in front of you and 6 is behind. Think of this thing like your room. So the first thing, if your electric field E is equal to E naught I cap. If your electric field E is equal to E naught X I cap, find the flux through each phase. If E is equal to E naught X I cap, E naught Y J cap, plus E naught Z K. Don't worry about ABC. Let's do A first. I want you to find flux on each phase. Remember, flux is integral E dot dA. A is the area vector. Think, whatever you can think, 30, 40 seconds, then I'll show you one. You'll get an idea. There's only one formula I taught you, integral E dot dA. That's it. Let's build things from there. Yeah, right, Samir. Got the first part. Neha, Srihari, that is wrong. Nero, yeah. I want each face. You're finding total. There are 6 faces for a cube. Sure, let me show you one. First time, right? It'll look a little confusing. Don't worry. It is easy only. You'll get it. What is the first question? The electric field is equal to E naught I cap. Okay, perfect. So let's draw the electric field first. So how is the electric field? Remember, it is going only along x-axis. So there is no field in y and z. So for phase 2, the electric field will be this way, E naught. For phase 1, also the electric field will be this way. For phase 3, the electric field will be this way. For phase 4, the electric field will be this way. Right? So the E is always like this. Now let's draw the area vector. How is the area vector for phase 2? This is the area vector. This is the area vector. This is perpendicular. This is the area vector, perpendicular. This is the area vector, perpendicular. This is the area vector, perpendicular, and this is the area vector. The green ones are the area vectors and the red ones are the field. Is that all clear, everyone? Able to visualize the picture? So think of the room you're sitting. The field is going in front of you. Okay, that's your I cap. So the wall in front of you has an area vector, the wall behind you has an area vector, and your ceiling, your floor, your right and left. They are the 6 faces. Able to visualize that? So your ceiling and your floor and your left and your right are in these 4 surfaces perpendicular to E and A bar are perpendicular. So if you see faces 1, 2, right? Faces 3, 4, 5, and 6. The E bar is perpendicular to A bar. So therefore flux is 0. And for phase 1, E bar and A bar are opposite. So minus E into A. But what is E? E naught. And what is A? A square. For phase 2, the flux in both are in the same direction. So plus E. So that is plus E naught A square. I hope everyone is clear what I'm asking now. Since the field is constant, you just get the field and multiply with the area. And you're done. All clear with this? Can you do the next one? E naught X I cap. Now the field is changing. Be careful with the signs. Huh? If the closed surface, sign matter karega. Because area vectors are defined. Right, Samyak. Okay, let's see. Don't be scared of E naught X. It just looks scary. It does nothing basically. So you should learn that. When you see a question, step 1, don't panic. If you panic, all right, the easy question will start looking like a monster. Now, the field here is E naught X I cap. Perfect. Luckily, phase 3, phase 4, phase 5, and phase 6 are still 0. Make sense? So the flux passing through 3, flux passing through 4, 5, and 6 are still 0. And look at phase 1 here. Huh? If you look at phase 1, this is an xy plane. X coordinate is 0. For phase 1, the entire thing is in a yz plane. X is 0. Therefore, field is 0. Therefore, flux is 0. There is no electric field only on phase 1. So there is no flux. So the only guy who's left is phase 2. This is your area vector, they're parallel. And if you look at this entire thing is again parallel to yz. So for this thing, x coordinate is a. So the entire phase 2, x coordinate is a. Therefore, the field is equal to E naught is E naught a. Therefore, flux on phase 2 will be E naught a into area, which is a square, which is E naught a cube. Is that clear, everyone? There is no need to integrate. Even though it looks like the field is changing, in reality, on a given phase, there is no field is not changing. The points where the field is changing, luckily, E become perpendicular to A. Isn't it? 3, 4, 5, 6, E is changing, but it is perpendicular. Phase 1 and 2, E is not changing, and E is anyway parallel, so it worked out. All clear with this? Now, using the same logic, we need to do for E naught X, E naught Y, E naught Z. So can I do this thing? I'll do for E naught X separately, I'll do for E naught Y separately, I'll do for E naught Z separately. Remember, flux is a scalar, so you can do for each one separately and you can just add them up in the end. You guys want to try? I'll give you a minute. Some have already got it. Let's see. You have all the three fields. So there is no need to do for all three at the same time. Do for each component, E naught X, E naught Y, E naught Z separately. And then just add them up. That should give you. Try, I'll give you a minute. So it's all about finding E dot A. That is the whole idea there. It's more of a math right now. Okay, let's see. Okay. So what I will do, I will take each component separately, okay? Phase 1, phase 2, phase 3, phase 4, phase 5, and phase 6. This is due to E naught Xi cap. This is due to E naught Y j cap, and this is due to E naught Z k cap. Perfect. So E naught X, the field is in this direction, right? So only 1 and 2 will be there. 3, 4, 5, 6 will be 0. So 3, 4, 5, 6 is 0. Why? Because E is perpendicular to A. 1 is also 0. Why? Because E is 0. Since E is 0, this is 0 we proved, and this is 0 because E is perpendicular to A. You're getting? I am finding due to each component separately. This is what we have done in the first part. And this guy is E naught A cube. Perfectly. It's great. Now for E naught Y, meaning field is this way, up and down, isn't it? You can clearly see 3 and 4 may there will be flux, and 1, 2, 5, 6 will be 0. So 1, 2, 5, 6 is 0. 4 is also 0 because E is 0. Remaining all are perpendicular. This is E naught A cube. Same argument I can do for Z also. 5 and 6 will work. 1, 2, 3, 4 will be 0. 6 will be 0 because E is 0. There is no Z coordinate there, and this is E naught A cube. You're done. So what is the total flux? Flux on 1, add all of them, 0. Flux on 2, add all of them, E naught A cube. Flux on 3, E naught A cube. Flux on 4, 0. Flux on 5, E naught A cube. Flux on 6, 0. You know how we did this? So do due to each component and then just add them up. Any doubts on this? Yeah, I think most of you did get it. Any doubts? All clear with this thing? Param, clear with this? Pratyasha? Advait? Vedika? Clear? Great. Let's see one more. Let's say we have a square plate at an angle, like an incline. Huh? This is theta. This is a square plate of side A. So this was A and this was A. The electric field is in the horizontal direction, E naught x I cap. This is your field. This corner is your origin. Meaning, if you look at the side view, right, side view will look like this. If you see the plate from the side view, it will just look like a line. This was theta and this was your E naught x I cap. Are you guys able to visualize how it is? Meaning, think of like this. So if you look into my screen, right? So this is the plate. So it is like this. Can you see? You think it is like a line, isn't it? But if you actually turn like this, can you see the surface? So there is a flat surface like this. And how is the electric field? Electric field is coming out like this. Are you guys able to visualize the picture there? Find the flux passing through the plate. Get me the magnitude. You can take area vector, whichever you want. So the in plate is at an inclined square plate of side A, inclined at angle theta. You have an electric field E naught psi cap. So why are we calculating flux? We will see later on. So calculating flux has a use. Mostly we'll be using them in the next class, but today it is all about flux calculation. E not cos theta, sin theta, cos theta, sin theta, a cube by 2. Okay, let's see. And that might look. Hmm. Hmm. Let's see how you guys took the area vectors. You have to be careful a little. No, Param, that is definitely wrong. So, listen, this was your incline. Okay. Let's say at a distance x, now be careful here. E is changing at every point. You have to integrate. You can't do directly E into area. E is not same. So we take a thin slice like this. But wait, x is already given horizontally. I can't do this. So this is not x. X is this. So if this is x, then we'll take a small piece here, dx. If this is dx, then this slanting length will be dx by cos theta. You have to be careful. X is already given. I can't take x along the thing because this is E naught x I cap. This is your x-axis. So I will take a thin strip because E is changing everywhere. I have to integrate where the width of the strip will be dx by cos theta, because if that is theta and this is small dx, and this side will be a, that will be the area vector, everyone. So in case you're still wondering how did I get this, look at the side view. So when you took a small slice here, I'm exaggerating the figure. This was dx, and this was angle theta. So that slanting length will be dx by cos theta. Let me draw a little bigger. This is how it looks from the side perspective. Perfect. So what is the area of this strip? So area of the strip dA will be side A into dx by cos theta. Great. And what about the angle? Now be careful. The area vector would be perpendicular to this. This is your dA. Whereas the field is this way, which is E. This is angle theta. This is angle theta. This is angle is 90 minus theta. So the small flux on the strip. So this is the area of a strip, thin strip. So flux on this thin strip. Now, because it is so thin, we can assume E is almost constant there, which is E naught x dA, the angle between them, cos 90 minus theta. Please check, see where you messed up. You have to be careful. The area ka value, the angle between them. So this is E naught and dA would be ax dx by cos theta sine theta. Perfect. So the total flux on the plate, I need to integrate this. Now there is one more trap here. This is E naught a tan theta integral x dx. What are the limits? Limits are not 0 to a. Remember, this was your x coordinate. And if the total side is a, this coordinate is a cos theta. So the limits will actually be from 0 to a cos theta. Is that making sense? The side of the plate is a, but uska horizontal projection is a cos theta. The x coordinate is only going from 0 to a cos theta. X coordinate is not going from 0 to a. So see where you did the mistake. Maybe you did a mistake by taking this as x. You can't do that because x is already given in the question, which is horizontal. So you have to play with that only. Right? So, and then you're done. So this guy would be E naught a by 2 tan theta. That would be x square. So that's a square cos square theta. E naught a cube by 2. Tan theta can be written as sine theta by cos theta. That's sine theta cos theta. I can multiply and divide by 2. I can create sine 2 theta. Yeah, you can manipulate all that. Please see. I think some of you have got it, I guess. Yeah. See where it went wrong. Again, it's not too difficult to solve, right, Trishi? Got it. But you have to be careful with the signs and angle. There is a chance of doing a mistake at multiple places. That's the only thing you have to worry. Clear? Take a break. Come back by 9:40. We'll continue from here. Any doubt so far? I took limits of integration. If this side is A, what is this horizontal length? A cos theta. So that is your x coordinate, isn't it? Because you have to integrate for x coordinate. So x coordinate is A cos theta. It's not A. Can't we do by joining the remaining area to get a closed shape? Yeah, do it and see if that works. It doesn't work. But why will you do that? What is the logic? What is the logic?
Sir, generally we do it. कि मतलब
Generally, what generally? I still didn't teach you anything. I don't know what generally you're talking about.
sir, the same field line passed through both of them, sir.
No, no, same lines are not crossing. When x is 0, E is 0. When x is A, field is EA. Where are the lines are crossing? Field is changing. It's not same lines. So we can't do it. Nah? Chalo, come back by 9:40. Yeah, let's go ahead. Cams on everyone. Let's do this one. Let's say we have a hemisphere of radius r. Let's say we have a uniform field. When you say uniform, meaning the direction and the magnitude is same everywhere. Find the flux through the curved surface. What is the flux passing through this curved surface? Right, you have it. You can just give the magnitude something, right? Yeah. So most of you got it. Let's see. Try others. Try. I'll give another 30, 40 seconds. नहीं होता. You have to be careful there. That was the trap. Param, right. Yeah, right. Now, see, the most common mistake, right, was this. People do like this. They think flux is E into area. So they will write E into 2 pi r square. Be careful. This is wrong. Why? Just look at this surface. You'll understand. How is the area vector? The area vector is like this. A bar, A bar, A bar, A bar, A bar. These are all your area vectors. And how is the field vector? The field is like this. E, E. You can clearly see the angle theta is changing. So theta is changing continuously. So when you write the flux formula, which is integral E dot dA cos theta, you cannot take theta out of the integral. You're stuck. Clear with this? If the theta had been constant, then you could have said E into dA and you would have got the answer. Clear why it is wrong? So technically speaking, we should take an element and integrate and do all that story, but there's a much better way. We go back to the definition. Now, forget about the sphere. We can do this for anything. See this thing. Let's say if you got a disk and let's say if you have some random amoeba shape like this. And this is the argument. Huh? For every field line that crosses this curved surface, if you just look at this disk here, you might think like, oh, what about this thing? Ask yourself, see, this is an entry. You entered from here. You exited from here. So that line is anyway 0. It is gone. The line entered and left. Now look at this. All the lines that pass through the curved surface, the flux passing through the curved surface is equal to the number of lines passing through the disk. Is that making sense? Right? So you can take any generic shape. So if you take your hemisphere, or if you take a cone, any of this shape, you will clearly notice every line that passes through the curved surface is passing through the disk. And since the number of lines are same, the flux must be same. That was our first statement of flux. Therefore, this area is called what? There's a name for this thing. It's called projected area. The first time we encountered projected area was fluid mechanics. We have discussed this thing in detail. So we observe. So again, the argument was this: the number of lines entering is equal to number of lines leaving. We observe number of lines crossing or passing. So this line, right, entered and left. So that will not be counted anyway. So when you say passing, we take the net lines passing through the curved surface. Right, and the shaded area are equal. This is also called as projected area. That means we can simply say flux is equal to E into projected area. So what is the projected area? The area which will make an open surface into a closed surface. In this scenario, that will be pi r square. But remember, this is valid only if E is constant. If E is changing, you can't do this. Valid if E bar is constant. The direction and the magnitude both must be constant. Only then you can use this. In case you forgot about the surface thing, the first time we used it was somewhere here. The projected area, page 40, yeah? Fluid mechanics. I'll keep it as a reference. You can check it out. There, the projected area has come. All clear with this? It's a pretty neat concept. You will get these kind of things in millions of bits. So let's see one more. This is an important result. You should remember them. Saves you time later on. Let's say we got a disk. Radius r on the axial line. You kept a charge q. This half angle is theta. Find the flux passing through the disk. Because see now, this q charge will have field lines, isn't it? So the lines are passing through the disk. So find the flux passing through the disk. The point charge is emitting field lines and they're passing through the disk.
We don't have the distance between charge.
I gave you theta and r, Nare. You can figure it out.
Right.
Hmm. Nee, Param, that is wrong. Right, Utsa, you got it. You have one answer. Anyone else? One thing is clear. E is changing, right? So it is always about choosing an element. This is something I keep telling you. Tell me one thing. See, देख के तो feeling आ रहा है ना, maybe integrate करना है. Can you tell me how to choose an element for a disk? So this is something I keep telling you. In physics, you barely have 7 to 8 shapes, and every shape has a specific way of choosing an element. So the moment you see a shape, you should know, oh, this is how I should take an element. So for a disk, how do I take an element? Anyone remembers? We take thin rings, yeah? You can do that also, but then again, you should know that concept. But to know that concept of solid angle, right, you should know the area. At the end of the day, you actually have to integrate. So better we directly do the integration only. Listen, how do we choose an element? At a distance x, take a thin ring dx. So due to this point charge plus q, the electric field will be like this. And the area vector will be like this. It's perpendicular to the thing. Let this angle be alpha. This is also alpha. What is the area of this thin ring? 2 pi x into thickness, which is dx. That is the area of this thin ring. What about the field? Let this distance be r. So the field will be kq by r square. So what is the flux on that ring? Flux on the ring will be E into dA into cos alpha. So E is kq by r square. This is 2 pi x dx into cos alpha. Perfect. So let's convert everything into x, since I know x ka limits. What is small r? Small r is, let this distance be d. Root over x square plus d square. What is cos alpha? Adjacent side d by root over x square plus d square. Perfect. Dump everything here. What is k? 1 by 4 pi epsilon. Q by r square is x square plus d square. This would be 2 pi x dx. Cos alpha is d by root over x square plus d square. This is a q by 2 epsilon d x dx by x square plus d square whole power 3y. This is the flux passing through the ring. You could have integrated in any other way, but yeah, this is what I could figure out. Right over here. Got it. Any doubt still here? If you got here, it is over, right? After that, it is max. If your integration is already done, you would have realized this is integration by substitution. So the whole idea is to get an element. You should be quite comfortable with this much level of integration. If you're struggling, that's okay, but that's what I keep saying. Resolve them. You should try them again. Integrate this thing. So this will be x dx by x square plus d square whole power 3 by 2. Remember, d ka value I still don't know. I can calculate it though. Then we say integration substitution, put x square plus d square is equal to t square. Differentiate on both sides. This thing I taught you in calculus also, but I think integration is done for most of you, so should be able to handle this much by now. That would be t dt. And then when x is equal to 0, t is equal to d. When x is equal to r, then t is equal to root over r square plus t square. Then your integral becomes qd by 2 epsilon. Integral limits will go from d to root over r square plus t square. X dx will become t dt. X square plus d square becomes t cube. You might be thinking like, oh, how will we know to do this thing? You will know how to do this thing if you had revised your notes. This is the electric field due to a disk. Integral x dx by x square plus z square whole power 3 by 2. Exact same integration. Nothing changed. right? So we have done this before. It's not like you're seeing this for the first time. T dt by t cube, and that would be qd by 2 epsilon. That will be 1 by t square ka integral. That will be minus 1 by t. Limits will go from d to root over r square plus t square. This is qd by 2 epsilon. Send the d inside. You end up with 1 minus d by root over r square plus d square. Yeah, the derivation is fine, but the result is more important. The flux due to the disk, if you remember, that is nothing but cos theta. Q by 2 epsilon 1 minus cos theta. You should definitely mug up this result. If you know the derivation grade exam, you won't have time to derive this. I'll write down this result. So the flux passing through the disk, so it doesn't depend on the radius, huh? It only depends on theta. Q by 2 epsilon 1 minus cos theta. This is the flux passing through the disk due to a point charge. All clear with this? Any doubts on the integration? So the main thing was this: choosing an element. You took such a thin ring, I can assume E is almost constant, and then you got the flux on a ring, and then we integrated for the disk. Clear? No. Let's see a question on this. Let's say we have a charge Q1 and we have a charge minus Q2. There are a lot of field lines between Q1 and Q2, but among them, there is one field line which is starting from Q1, and we know, right, lines emanate from Q1 and they converge at negative charge. The field line leaves Q1 at an angle alpha and enters Q2 at an angle beta. A particular field line. Find the relation between alpha and beta. And the whole question looks like, what the hell, right? First time when I saw, even I felt the same thing. I was like, what the hell are you even asking? But think. So there are a lot of field lines. This is one of the field lines. So a field line leaves plus Q1 at angle alpha. And this is the kind of a question I should have seen before. नहीं तो idea ना थोड़ा difficult है. At an angle alpha and enters minus Q2 at angle beta. Find relation between alpha and beta. You need the previous result, huh? You will need this result. So that much I can tell you. Think, take a minute or two. Forget about getting the answer. I don't care. You also don't care. Just think for a minute or two. What the hell is happening? How do I even start? What is this? Anything. And that is more important. Don't run behind the answer every time. Once you become strong, once you're capable of thinking, you will start seeing things. Arya, you did figure out. Guessed it, or you have a solid logic like why? You have a solid logic. ठीक है. Listen, the logic is pretty straightforward. So the idea is this. Now, by symmetry, we can also say there will be one more line going at the bottom also. This also will be alpha, this also will be beta, because there is a symmetry there. Now what we will do, we are going to consider a disk very close to the charge. Okay, you take it very close. Consider a disk very close to the charge where these lines become almost, touching the edge. Consider a disk very close to the charge. It's important to take very close to the charge so that the line will be almost tangential. Similarly, I can consider a disk very close to the charge. And from here, can I argue every line that passes through this disk has to pass through this disk? Is that making sense? Because you are saying this line is the edge of the disk. This line is the edge of the disk. That means all the lines between these two must be passing through the disks. And we proved the flux passing through the disk does not depend on the distance. It depends only on the angle. So I can keep the disk wherever I want. I'll keep it very close. Right? So we observe the number of lines passing through the disks is same. This is what I said, the first statement. If the number of lines are same, flux is same. The number of lines passing through the disks are same. Therefore, the flux has to be same. And what is the flux passing through the disk? Q1 by 2 epsilon 1 minus cos alpha. What is the flux passing through this disk? Q2 by 2 epsilon, just the magnitude, don't worry about the sign. 1 minus cos beta. There, you're done. So Q1, 1 minus cos alpha is Q2, 1 minus cos beta. Does it look easy now? That's because you know the result. If you don't know the result of the disk, this will be difficult. Any doubts on this? All clear with this process? Let's see one more like this. Yeah, I mean, once I said it is based on the disk, you'll get it. These will be good advanced stuff. Let me show you one more. Let's say we have Q1. This is let's say this is Q1 and this is Q2. Now a field line leaves here at an angle of 60 degrees. And then because both are positive, this line is going to bend here and goes off to infinity. Because both are positive, the field lines will repel from each other. It will bend and go off to infinity. And if you join these two, and if you extend this line from infinity, this angle makes 30 degrees. Find Q1 by Q2. You never thought, no, we can play with field lines. These things will open up your way of thinking, and also the ideas are important. So, I'll give you 2-3 minutes. Forget about the answer, like I said. Now, if you're feeling like, oh, what the hell is this? Think of it this way. What happens if this comes in the final exam? Better you get slapped right now in the class. Think. Again, I'm telling you, you have to use the Disca formula. Story to wahi hai. You will need the Disca formula. Now, up to you, how do you interpret this? This is how our advanced revision program will look like. This will be a starter problem there. Because by then you guys also will be strong, na? Because by then when I give this question, you will know the answer for this. So that is the whole point. Think. How will you figure out? So a line which came at 60 degrees took a turn, went to infinity. When you extend the line, it met somewhere. We don't know where it met also, but it made 30 degrees. This much we know. Using this one picture, you have to tell me what is Q1 by Q2. Nee, Srihari. Even I don't remember the answer. It's a little complex. Let's see. I don't think you'll get such a good answer though. Shaurya, you got two. मुझे exactly याद नहीं है, but I remember there'll be some root 3 somewhere. I don't know, Srihari, if you have to see. 2 minus root 3. Because I said root 3, people are giving root 3s. Let's see. Think. I'll give another minute or two then. Okay, and we also got 2 minus root 3. But interesting, huh? How did you guys even end up with 2 minus root 3? Shaurya, how did you get 2 minus root 3? Batao. Bol na. Unmute and tell me na. Because most of you got 2 minus root 3. I want to see what you guys all did.
Sir, like I just used like trigonometry thing.
क्या
So
था
like,
trigonometry?
sir, like वो रेशियो को 1 माइनस cos अल्फा और 1 माइनस cos बीटा के टर्म्स में लिख के ट्राई किया सॉल्व करने का, तो उससे जो है वो बोल दिया.
But how did you do that, na? Because ये question में एक plus था, एक minus था ना. That line came to here. This line is not coming. This line is going away.
Like going.
And देखो ना, दूसरा ये जो angle है ना, that angle is coming from here ना. Angle यहाँ से 30 नहीं था. How did you guys even use that? Okay, listen, see. Let's see slowly, one step at a time. So the thing is, let's consider, we know by symmetry, right? There'll be one more line at the bottom also, which will go off like this. Great. This is also 60. Now consider a disk very close to this charge. So that story is still the same. Okay. So if I just exaggerate this, it would look something like this. So that is the thing there. So what is the flux passing through this disk? Now see, every line that comes from here would go something like this. That is how the flux will go through the disk. So flux passing through that disk is Q1 by 2 epsilon 1 minus cos 60, or Q1 by 4 epsilon. Perfect. That means all the lines that are going in the other side, so they are going like this. How much is that flux then? That should be the remaining flux, isn't it? That must be the remaining flux which is passing through here. So this flux, which is not going through the disk, or flux between the two boundaries, right? Flux between the two, whatever that lines. must be the remaining flux, which is Q1 by epsilon minus Q1 by 4 epsilon. That's the balance flux. Because if I take theta is equal to 180 degrees, I will get how much flux? I will get Q1 by epsilon. No? That was a total flux. That's a total minus this. So this is 3Q1 by 4 epsilon. इतना clear? Any doubts on this? Flux passing through the disk is this. Flux between the lines or flux not passing through the disk is this. The total must be Q by epsilon. How did I get Q by epsilon? If you make the theta 180, you will actually get a full sphere. So we can prove that also later on. I'll show it in a much easier way. This is not passing through disk. Any doubts on this page? Flux between lines, could you explain again? देखो ना यहाँ पे Trishi. This one, the one which I'm drawing in black, this is the last lines which are touching the disk, isn't it? All these green lines are passing through the disk. Agreed? Which was Q1 by 4 epsilon. That means all the remaining lines are not passing through the disk. So those things are between these black lines ka boundary, isn't it? So can I argue from the total flux, if I remove the flux from the disk, that should be the balance flux? Sure. The flux between the lines will be the total. So this term here is your total flux. Q1 by 4 pi epsilon is flux through the disk. If you subtract them, you'll get the balance flux. So far clear with me? It looks tough for the first time. Once you get the hang of it, later on, no matter what kind of weird shape I give, the idea is always the same. Now, you said this is Q1 and this is Q2. And now if you take a person at infinity, and if you ask him, boss, what do you see? What do you think he will say? If you put a person at infinity and if you show him these two charges, what do you think he will say? He will say, there must be one single charge here, Q1 plus Q2, and the lines are coming from here, and these things are making an angle 30 degrees. This is what he will think. Is that making sense? So a person at infinity sees a single point charge. Q1 plus Q2. So these are the black lines, okay, the boundary lines. And now if you ask him, okay, how much is this flux? He will say, this flux is nothing but Q1 plus Q2 by 2 epsilon 1 minus cos 30. So far clear? Now can I argue the total number of lines that are passing between the black lines and the total number of lines passing between these two black lines must be same because they are one and the same. Is that making sense? The flux between the black lines in this scenario, when you have taken Q1 separately, and the flux lines when you take Q1 plus Q2 separately, because these are the same field lines, it is just your interpretation from infinity that it feels like, you're just looking a point charge. The flux between the boundary lines or the black lines here, I'll just call it black lines, in both the scenarios must be same. Whether you think it is a point charge or whether you think it is like one Q1 charge are same. That means the flux must be same. Therefore, the previous flux was how much? 3Q1 by 4 epsilon must be equal to Q1 plus Q2 by 2 epsilon 1 minus cos 30. Solve this, you'll get the answer. Again, don't worry at all if it really went over the head. It's pretty normal. The whole chapter will look like this only. You'll get used to it by next class. That is the whole thing. हाँ आर्या बोलो ना.
Sir, I didn't understand why you equated it to 3q1 by 4 epsilon.
Because ये between the black lines flux क्या था?
Sir,
3q1 by 4
3q1
epsilon
by
ना.
4 epsilon.
No, when you're standing at infinity, आप क्या देख रहे हो? You're looking at these red lines only ना.
Sir, then what happened to the green lines?
They went away to the right side.
Oh, okay.
वो तो right side चला गया ना, इस side चला गया वो.
Yeah.
I don't know
Okay.
what happened to them. They went somewhere and they died. Who cares? Clear with this? Mm, good one, right? So you can play with this thing. I can give different charges and you can do all that stuff. So let me show you something. Remember this thing, the field generator? So let me put a more field lines. So there. So I'll put a positive charge. So this blue dot is one positive charge. I'll keep one more positive charge a little far. I can put more. I can click multiple times. It becomes more charge. Great. And now if I start the field lines, look at the field lines. So they're coming as they approach. Now they start bending away. दिख रहे field lines? So we are talking about somewhat in this region. So let me just. There we are talking about a field line, something of this sort. The line which went away, something like this. Then when you extend this, this was your 90 degrees. You able to see these field lines here? That's how the picture would look like. I gave you this link, right? You can always play around with this thing. It's a beautiful thing. I liked it. You could have actually played with this with a positive and a negative. Let's see how will that look like. Positive, and this was your negative, and there you can see that one angle is entering at alpha and beta. This is the disk equation. You can see all this stuff. Perfect. But should, yeah, definitely give it a try. Later on, think about it. It's a good one. All clear with this? Great. Let's do something simple to make you happy. So we got a sphere of radius r. There is a point charge at the center. Find the flux passing through the sphere. I don't know if you know the result, but let's prove it with an integration. Okay, let's see. Yeah, this would give a very good result actually. This will be the foundation for us going ahead. So consider any one point here, some random point here. So the field will be radial. At that point, the area vector also will be radial. So if you observe, no matter which point you take, the field vector and the area vector are always parallel. E bar is parallel to dA bar at every point. Therefore, when you take the flux integral E bar dot dA, that will be mod E bar, mod dA bar, angle between them is cos 0. That would be simply mod E bar integral mod dA. So this would be q by 4 pi epsilon r square. And this would be 4 pi r square. We end up with flux is equal to q by epsilon. It doesn't depend on the radius. No matter how big speed you take, it remains the same. Clear with this? The 4 pi r square will cancel off, Renisha. Forgot to multiply with an area there. Clear with this? And little more context here. I hope you guys remember what is integral mod dA and what is integral a bar. So if you take a sphere like this is the area vector. Okay, the vectors are like spike, the spikes like balls, like a spike one. Can you tell me what is the difference between integral dA bar and integral mod dA bar? They're completely two different things. Just ask yourself, dA bar is a vector. What are you doing? You're doing sum of all vectors, isn't it? If you add all these vectors, for every one vector, there's an opposite vector. You'll get a 0. Isn't it? Because this is sum of all vectors. But what is mod dA bar? Mod dA bar is an area of a small patch, which is a magnitude. If you add all these patches, this will give you the surface area, which is 4 pi r square. Hope you're seeing the difference. Mod dA bar and this thing are completely two different quantities. Just putting a mod will change the whole meaning of it. Great. So we got pi by q by epsilon. Now listen, something more interesting happens. So that means we proved if you take a sphere and if you put a charge in the middle, we get the flux is q by epsilon. And the best part, what if you take some amoeba shape? You take some random amoeba shape. Now, can I argue every line that is passing through the sphere, the same number of lines, also pass through this amoeba shape? Since the number of lines passing are same, then the flux must be same. So flux passing through the sphere must be equal to flux passing through any closed surface here. Which is q by epsilon. You cannot integrate for any random surface, but you can argue with this statement since the number of lines are same, the flux is same. There we proved a very important thing. That means you take any surface, the flux is simply charge enclosed by epsilon. The number of lines is same. So we can make an argument. So we're actually proving Gauss law from here. But if you see history-wise, right, Gauss law came first and then came Coulomb's law. So flux through any closed surface is simply the charge enclosed by epsilon. We will talk about what happens if there's a charge outside also. So for example, let's say we have a closed surface. Let's say this is Q1, this is minus Q2, this is Q3, and this is Q4. And someone asks you what is the flux through the closed surface? It should be closed surface, huh? That's important. then this will be simply Q1 minus Q2 by epsilon. The outside charges won't matter. And we will see that why in the next page. And we proved it with a sphere because see, if you give any random surface, I don't know how to calculate, but I know how to calculate for a sphere because sphere is special. And then we'll argue number of lines are same, so the flux is same. I hope you're getting it. How we are combining that both the statements everywhere. You can calculate flux using only electric field, but you can relate that flux to any other shape saying the number of lines are same. Clear with this? So one thing about this chapter, right? It's not tough, but it's a lot theoretical. Most of the questions, right? You prove it by arguments because this happens, and because of this happens, that happens. And that's what makes the chapter a little difficult for people normally. Now, what about a charge outside? Suppose if you have a closed surface and if you keep a charge Q outside, again, notice this. Every line that enters leaves. The number of lines entering is equal to the number of lines leaving. Therefore, charges outside do not contribute to any flux. Therefore, flux on a closed surface due to outside charges is zero. The outside charges won't matter. Clear with this? Now, this will be a statement question, more than one choice, but they'll ask you this thing. What about flux at a point? Flux at a point is different from flux on a surface. Most people remember that one statement, outside charges do not create flux, and exam they'll ask you flux at a point can be positive, can be negative, it can be even zero. What do you mean by this? So if you just take a small area, look at this surface here. So this was your field. This was the field and this was the field. If you consider a small area vector here, look at this. This will be your dA bar. The angle theta is acute. So at that point, flux is positive. So there are some points where the flux is positive, it is entering. Some points the flux is leaving, it is negative. So flux at a point is different. Yeah, what am I writing? Acute. So here flux at a point is positive. Look at this thing here. Area vector is this way. This angle is obtuse. So when it is entering, flux is negative because we take outward normals as positive. You will even find a point, a special case where the field lines become a tangent 90 degrees. So flux can be zero. So be careful with this statement, everyone. Flux at a point, flux on a closed surface. These are two different words. When you say closed surface, you're taking the total. So mathematically, E bar dot dA need not be zero. But integral E bar dot dA becomes zero because that's a total flux. This is flux at a small patch. We call it flux at a point. We put a small circle here. It's a closed integral. We'll talk about that later on. Is the story clear so far, everyone? If it is not closed, there is no outside and inside. Clear with this? So this is the thing. Okay, this will be the foundation for us in the next class.
Sir, if there is no outside and inside, then how can we find the direction of this aerial vector?
You are in the class, right?
Yes, sir.
And then what were you listening? For any open surface, we choose area vector in the direction of E bar. So it can be anything, random. There's no defined direction for it. Yeah.
Sir, so the area of electric field is equal to the area of material
Your voice is
pressure,
breaking a lot, Srihari. I can't hear.
direction
Can
of
you just type it? Can you just type it? I can't hear your voice. You're breaking.
oh,
Just type it. Okay, so that is one thing. Again, I'm telling you, please make sure to revise today's notes, gravitation and Gauss law. Gravitation, we did some really good stuff. Last class of gravitation, we had that 4 problems, and today we had the 3 problems. And Gauss law, please revise the notes and come. It's not a tough chapter, but if you really don't understand what is flux, what is line, how to calculate flux, you will have a problem going ahead, right? So when we catch up on Tuesday, we'll continue from here. We will do more of this. We will calculate flux for even more different shapes. And then we'll see, like, actually, how is this even useful? Like, what do we actually use this for? So we'll work on that. Again, not a big chapter, but quite an important chapter. The ending of Gauss law is the beginning of capacitors. That will be the introduction for the next chapter. I think we should take another 3 to 4 classes maximum. So, okay, with that, we'll wrap up for the day. So, any doubts, anything else, please stay back and ask. And do remember, there's a test online for tomorrow. So make sure to give it. I'll see you guys again next Tuesday. So take care, stay safe.